triangle inequality starts off and says you're in some geometry, and then you're looking at three distinct points in the geometry. So say you have points A, B, and C here. You then take those points and you form three line segments, and these are all the line segments that could be formed from those 3 points. So you have AC, AB, and then BC. Now, you have a couple situations that could happen. You could happen that all 3 of these points live on the same overarching line in the geometry, and in that case it just looks like a big straight line. Or you could have these 3 points to be non-collinear, which means you're essentially forming a triangle, hence the name. So let's see what happens here. So if you look at collinear points, so say you're looking here at A, B, C, where B is the one in the middle. So here's B, here's A, here's C, just to give ourselves a little bit of a reference point. And this one here says that if you take the sum of AB and BC, that's going to totally be the entirety of your line segment AC. Now, the reference here says this is always going to be true if B is between A and C, and this is by our third congruence axiom. And just to remind ourselves, that third congruence axiom right here, C3, says you start off with 3 points on a line, B is the one in the middle, which is exactly our situation here. And then it has some other stuff that looks totally complicated. And remember, if you're in a geometry that has a distance function, that is exactly the same thing as saying the distance from A to B plus the distance from B to C equals the distance from A to C. And remember what that actually means. If you have a distance function that gives you your line segment congruence, that actually is telling you exactly this same situation that we just had in our triangle inequality, which says the sum of 2 of the line segments equals the third line segment. Okay, so just by the fact that our assumption is we're in a Hilbert plane, or at least we're in a Hilbert geometry where we have the incidence axioms between its axioms and the first 3 congruence axioms, you're going to be able to cite C3 and say, hey, this first bit is obvious. But what happens if these points actually got jumbled? Okay, so suppose you have this second situation where you've got now point C is in the middle, and this is the same exact idea if you had A be the point between the other 2 as well, so we won't go over that case. So technically you have a third case that we'll ignore. Okay. Well, according to what we just said with our third congruence axiom, this would give us that AC plus BC is going to equal the overarching AB. Okay. Now, is that the same thing as what we have from our triangle inequality? No, but we can get there. So the next step is to say, hey, well, think about what it means to be less than or equal to each other. So if we have this situation where we've got our point A, our point C, and our point B, by the fact that C here is between points A and B, remember that means that line segment AC is considered shorter than line segment AB or less than line segment AB. So then, if you add on any line segment, in this case BC, that is automatically going to be true just by the definition of line segment inequalities. And you do the same exact thought process here if you wanted to put point A in the middle. Now, what happens if these 3 points don't live all on the same line? Suppose they're non-collinear, in other words, they form a triangle, and in that case, it depends on which model you're in. So the rest of this part that I'll look at the triangle inequality when the 3 points A, B, and C are non-collinear, I'll specifically look at our Taxicab model on R2. And just to remind ourselves of the Taxicab model on R2, Taxicab model said with R2 here we had what? Well, we had points which were real points in the real numbers in the x and y coordinate. Lines were straight lines between us defined in the normal way. And the main thing was we had a distance function that gave us line segment congruence, and our distance function was defined as the absolute value of the change in x value plus the absolute value of the change in y value. So there's our starting point. Now, when we then look at our 3 non-collinear points, there's a couple different situations. The first situation is, suppose that we are able to look at this line segment AC and we are able to compare it to AB and or BC. You'll actually always be able to compare it to both. That's one of our propositions in section 8. And we actually find that AC is shorter than one of the other two line segments. Don't overthink it. In this case, we're done. Okay. Immediately, if AC is shorter than one of the other two line segments, if you add something extra over here, of course it's going to still be smaller than the sum. So really we can look exclusively at the situation where AC is your longest of the three line segments to see if it would work, see if we would actually get this triangle inequality in that setting as well. Okay? Because the triangle inequality didn't specify that side AC was longest. It could have been any of your three line segments that were formed. So, first case. First case is what happens if AC is your longest of the three sides and you get, well, a little right triangle here. So the other two sides are vertical and horizontal. Maybe it's not this exact picture, but it's this idea, okay? Well, what happens with Taxicab model? Well, we know that in the Taxicab model, that third congruence axiom is satisfied, which means that the distance from A to C is in fact going to be what? Well, it's going to be, well, this looks like third congruence axiom, but it actually is just applying the Taxicab model's formula. So distance from A to B is your change in y coordinates. Your distance from B to C here is your change in x coordinates. So because we have this vertical and horizontal line, we get an equals here, and we're just adding those guys that only had a change in x value, only had a change in y value. Now, notice what this means by definition when we throw this into the congruence. We just say, all right, well, our distances were the same, so of course we get that our line segments work out. And notice this is one of the cases right here of this less than or equal. The or equal part is telling you that either AC is congruent to the sum of A, B, and BC, or it's strictly less than. Okay, this is the situation where it would be congruent, where you have both, or essentially you've got a right triangle and the two legs are vertically and horizontal. Two legs are vertical and horizontally oriented. Now, you can also have the same situation where we're going to have three non-collinear points. So again, we're going to form a triangle. We're still assuming that AC is the longer of the three sides, but in this case, you don't have the other two shorter sides of the triangle to be one vertical and one horizontal. Okay, so in this first picture right here, AC is still visibly the longest of the three sides. One of the sides is horizontal right here. This one down here, all three sides are not horizontal, not vertical. And this bottom one here, actually I probably should have reoriented this one a little bit, but we've got one horizontal side. It actually turned out in this case what looks like AC, and it looks like in this particular case I really should have relabeled it to grab it the longer one. Well. Alright, so let's see what would happen here. In this particular case, or really in all of these cases, and this actually works in the other one as well, if you have the distance from A to B, so I'm just going to pick on this, how about this middle one right here because it's right next to case 2. The distance from A to B is, you're going to do what? You're going to do change in x and change in y. So we go part way around this dotted rectangle. Then if we look at the distance from B to C, notice change in x, change in y. So again, we travel from point B and go a little bit further around the rectangle. And then if we look distance from A to C, well, I'm actually going to start at C, but here if we do change in x, change in y, notice we get back to the starting point of A. And my claim is that will always be the total perimeter of this rectangle. Notice your points, all three vertices of the triangle, all 3 points A, B, and C have to be on the perimeter of this rectangle. You can't just randomly have any old rectangle. These dotted lines have to actually mimic where the change in x and the change in y would be calculated from. Now if we look at this other case up top, notice from A to B, so distance from A to B, we go up and around the corner of the rectangle. The distance from B to C, notice here, in this one we only go on one part of the rectangle, and C back to A, again we go around the rectangle. And same deal down here. We go up and around the rectangle, go up and around the rectangle, and then we go all the way back. Okay. Now, once we've looked at our total perimeter of a rectangle, there's a couple of things that you can look at. If we focus in on AC, and I'm going to go ahead and focus in here on AC, my claim is that it will always be the length of one of the sides of the rectangle, and that's because it's the only way it will happen with these type of rectangles. You'll have change in y, change in x, and if these dotted red lines here indicate those change in x's and change in y's of the points, you're forced to have at least one side of the rectangle for this longest guy. Now, up to the length of the second side, well, this first case is where you actually get one side plus the second side. This middle one is where you've got one side plus a little bit on the second side. And this other extreme case, and this is why this last one actually came in, was where it was just the one side. Okay. Now, what happens if you know that the distance from A to C must be the length of one side of this little dotted helper rectangle plus somewhere between 0 to a full complete second side? Well, that means the following. It says, hey, this means that AC, the largest it could possibly be in the value, is half the perimeter of the rectangle. Well, when would it be exactly equal to half the perimeter of the rectangle? In this first case right here, where it's actually you're changing x and changing y, correspond to two sides of your rectangle. And notice both of these other two situations are something smaller than that. Okay. Now, if we then want to look at our sum of the distance from A to B plus B to C, remember here we said that the sum of all of these distances, in other words, adding up the lengths of all three of the sides, is exactly the same as the perimeter of the rectangle. Well, if the length of side AC is less than half the perimeter of the rectangle, that means the other guys have to be, well, everything else. So if it's strictly less than half the perimeter, this sum has to be greater than half the perimeter of the rectangle. And if it actually equals half the perimeter, like in this first case, then this sum would also equal, well, half the perimeter, which gives you exactly the result that we wanted right here, namely that inequality. Then using the definition of line segment congruences relating to distance functions, we get exactly our triangle inequality. And that's it. That's how you would show that the triangle inequality holds in the Taxicab model. Now, triangle inequality does in fact always hold in our standard model. It was known by Euclid. It's actually in Euclid's Elements. It's proposition 20 in Euclid's first book. However, with the soup and the double model, those two models that we've been looking at, you would then have to also verify this same process, and you'd say, all right, well, in those cases, our distance formula is a little bit different, so what would we do that would change? And it turns out not both of them does the triangle inequality hold, and what you'll be able to do is if you were looking to see if the triangle inequality hold in either of those two other models, if it doesn't hold, you could find a counterexample. Namely, you could find a triangle where the sum of the shorter two sides is in fact smaller than the length of the longest side.